Hi there, welcome to lecture 13 of Machine Learning from Data, Validation and Model Selection. Now these are not very hard concepts, but they're very important, useful concepts. So you definitely want these tools in your bag. Now before we get going, as usual, let's have a quick recap. We're talking about overfitting. Overfitting, there's noise in the data, your learning algorithm tries to fit the noise, and in so doing it gets led astray and outputs nonsense. Okay, now regularization comes along and basically puts a leash on the algorithm, basically applies the brakes, okay, prevents the algorithm from fitting the noise. And here's how it works. Okay. Instead of minimizing just the in-sample error, you minimize the in-sample error plus a penalty term. Okay, and we call this sum that you minimize the augmented error. Now, let's look at this penalty term. There are two important parts. The first is what we call the regularizer omega of h. That's basically how you choose to measure the complexity of your hypothesis. And you should pick this penalty term so that it encourages smooth, simple hypotheses. Now, what's the idea there? The idea there is that noise is rough and complex. So by adding a penalty for complex and rough hypotheses, you're preventing your ability to fit the noise. Okay? And there are many different regularizers, and the key here is that we'll pick in practice some standard regularizer like the very popular weight decay regularizer that we talked about last time. Okay? And then the key is to pick the right value of lambda, the right amount of regularization. So that's the other term in this penalty is this lambda called the regularization parameter that determines how much regularization. And that's the really important term, not so much, the type of regularizer, because there are many standard regularizers that encourage smooth, simple hypotheses. The real key is how much regularization do you want? And you can see from these pictures below, which we showed last time, that if you have no regularization, you completely overfit the data and output nonsense. If you have just the right amount, and in this case a very small amount of lambda, a very small amount of regularization, you get almost a miraculous fit. Okay? But as you add more and more regularization, you start underfitting. Okay, so the optimal lambda is basically balancing overfitting with underfitting, balances approximation with generalization. So on the left, you approximate the data well, but you don't generalize. On the right, you don't approximate the data well, but okay, that performance that you get in sample is gonna be, the same kind of performance you get out of sample. Bias and variance. So, large lambda will have small variance, but high bias. Small lambda will have a smaller bias, but very high variance. Okay, so you can view the choice of lambda through all these various lenses, and it would be very useful to have a tool for picking lambda. Okay, so let's get to validation. And one of the uses of validation is to pick this sort of optimal lambda, or give some principled approach to picking this optimal lambda, as opposed to just guessing 0.0001. Okay, so let's talk about the high-level idea for validation. Now, you have the out-of-sample error, E out. Okay, and we can generally write the out-of-sample error as the in-sample error plus, let's call it an overfit penalty. Now the VC bound, attempts to bound this overfit penalty with omega of h. Okay, and regularization estimates this overfit penalty with lambda over n omega of g. Okay, so one is VC gives a complexity to the hypothesis set, a complexity penalty for the hypothesis set, and regularization gives a complexity penalty for the hypothesis. Okay, now what does validation do? It just goes all out. It goes all out for the out-of-sample error and says, forget about estimating an overfit penalty. Let's just try to estimate the out-of-sample error directly. Okay, that's what validation does. Okay, now in general, bear in mind that if we can get an in-sample estimate of the out-of-sample error, that's really the holy grail of learning from data. Okay, if we can do that, we've solved the first step of machine learning, the E into E out. We don't need E into E out because we've got E out, and we can directly look at E out. Okay, so that's the goal of today, is to see to what extent can we get can we directly try to estimate E out from the in-sample data. Okay. And then if we can get an estimate of E out from the in-sample data, we can certainly use this estimate for different choices of the regularization parameter lambda, and that'll give us a principled way to pick the regularization parameter lambda. Pick the value of lambda that minimizes the E out. And how did we get E out? Because we have an in-sample estimate. Now, I'm not promising you that we're going to get an in-sample estimate. I'm just saying that if we could, it would be very, very useful. Okay, so let's get into the details and go to the board. Okay, so we're after the out-of-sample error. Okay, so let's see how we would go about getting that in an ideal setting. Okay, so here's the setup. You have a data set, Dn. Okay, and you run this data set through your hypothesis set and learning algorithm, and you produce a final hypothesis G. Okay? And this final hypothesis G has some out of sample error E out of G. And we would like to get a handle on this E out of G. Now I'll remind you what is E out of G. E out of G is the expected error on a randomly generated out of sample data point. Okay? So you generate a random data point X, the out of sample data point. Okay, you evaluate G of X. Okay? And you compare that with the Y value and compare meaning compute the error. Okay? And this is in some sense an estimate of the out of sample error of G. So let's call this E of G. Okay, so I'm ignoring the fact that X and Y are these randomly generated data points. It's really the error that G makes on a test point. Okay, and you know the expected value of E of G is equal to E out of G. Okay, so now it's important to realize that this is the expected value of E of G. Okay, whereas when you just generate one data point, yes, on average in expectation you're gonna have an estimate for E out of G, or that's the definition of the out of sample error E out of G. But on a single data point, this thing is going to be random, in some sense wild. Okay, so there's going to be some variance. Okay, so there's going to be some variance of E of G. So that's not very nice. If we tested G on just one data point out of sample, it could look good, it could look bad. On average is what we want. Okay, so what's the solution here? So the solution here is don't just generate one data point out of sample to test your final hypothesis and to evaluate its out of sample error. Generate a bunch of data points. So let's imagine that you generated k test points. Okay, so you generated k test points, x1, x2, up to xk. Okay. Well, since these are test points, these are out of sample points, let's call this the test data set, D test. Okay. And so, you have your test data set. Nice. Very convenient. Okay. And now what we can do is we can evaluate G on each of these test points. Okay. So imagine that when I evaluate G on test point x1, I get an error E1. Okay. Along with these test points are of course the Y values, so I'm going to get E1. And then if I evaluate on x2, I get E2, and so on. I can get E1, E2 up to EK. So what's the error made by my final hypothesis? On k test points, let's call it capital K. Okay, and the error made is it depends on what's the application. If it's classification, it's the number of mistakes. Okay, so these are each either correct or a mistake. If it's regression, it's let's say the squared error and so on. Okay, now what would I do? Okay, well, I've got k test errors, okay, and it certainly seems the right thing to do to take the average, because I'm interested in the expected out of sample error on a test point, and that should be approximated by the average of these test errors. So what I can do is I can compute E test, which is equal to 1 over k, the sum from little k equals 1 to big K of E little k. Okay. And this we call the test error. This is the test error. Okay. Now, it's certainly very appealing to use the test error as an estimate of the out of sample error of G. Okay. And let's see how this behaves. Now, if you're in classification, you could use the VC analysis and so on and so forth. But let me use a sort of analysis that's applicable in general. So we're going to look at the expected value of the test error, and then, how good is it as an estimator of E out can be captured by its variance. Now, the error on a single point has the correct expected value, and it has some variance, which could be large. Depends on the, distribution of X and Y and so on and so forth, okay? But now let's look at the test error. So the expected value, and you should be able to do these calculations quickly, hopefully. So the expected value of the test error is equal to the expected value of the test error is equal to the expected value of 1 over k, the sum from little k equals 1 to big K of EK. Okay, and expected value is linear, so I can pull out the 1 over k. So I get 1 over k expected value of it's linear, so I can pull out the k and take the expected value into the summation. So it's the sum 1 over k, the sum from little k equals 1 to big K of the expected value of EK. But each of these EKs is exactly the error made on a random test point. And let's assume that I've generated these test points IID. So these are IID. Okay? It's not necessary for this step, but it'll be necessary for the next step. So, you know, I have expected value of EK, which is the expected error on a test point. Okay, so this is exactly the definition of E out of G. So this is equal to 1 over K, the sum from K equals 1 to big K of E out of G, which, you know, is the sum of E out of GK times divided by K, which is just E out of G. Okay, and no surprise here. Okay. The expected value of this test error, which is the average of the errors made on the test point, is exactly E out, which would have been the average, which is the average of which is the expected value of the error made on any one point. Okay. Now, where do we gain with the test error? We gain in the variance. So this guy may be large, maybe it may have a huge variability, but let's look at the variance of E test. Okay, now this is equal to the variance of what? Of 1 over K, the sum from K equals 1 to big K of EK. That's E test. Okay, now you need to know something about variances. The variance of, you know, a scalar multiple of something is this scalar multiple squared times the variance of what's inside, what it's multiplying. So this is 1 over K squared, the variance of the sum from K equals 1 to big K of EK. Okay, which is, now comes the important fact that the data points are IID, so they're independent. So these EKs are independent. So this is 1 over K squared times the sum from K equals 1 to big K of the variance of EK. Okay, and that's because the variance of a sum of independent random variables is the sum of the variances. Okay, but now this variance is just the variance of the error made on a random test point. That's exactly what we call variance for E of G. Okay, so this is exactly 1 over K squared, the sum from K equals 1 to big K of the variance of E of G, which is, there are K copies of the variance added together, so you get K times the variance, but divided by K squared. So this is 1 over K times the variance of E of G. Okay. All right. So we did all this analysis for what? Okay. So the test error is an estimate of the out of sample error. Okay. So let's summarize. Okay. So the expected value of the test error is exactly equal to E out of G, and the variance of the test error is exactly equal to 1 over K times the variance of the error on a single test point, E of G. Okay, so summary. Okay. What does this tell us? Well, it tells us something that we should probably be very familiar with. It says that your test error is an unbiased estimate of the out of sample error, and it tells us that its variance is decreasing with K. Okay, there's this fixed term, the variance of the error on one point, okay, but then it's decreasing with K. Okay, so the error, you can think of the error bar, roughly speaking. The error bar in this estimate, so E out is sometimes we will say is approximately E test, okay, plus or minus 1 over square root of K times the square root of the variance of E of G. Now this is a heuristic statement. We can make probabilistic statements, okay, using something like the Markov or Chebyshev inequality, but basically what we can see is that the out of sample error is approximately equal to the test error plus a term that's decreasing like 1 over the square root of K. Okay, good. So that's nice. We have this nice test error, which is an estimate for the out of sample error that gets more and more accurate as you increase the number of test points K, except that this is a fictitious world. This is not a real world. And for the simple reason that we do not have the ability to generate this test set. Okay, so this ability we don't have. Okay, so we need to come back to the real world and ask if we can perform something similar to this in the real world using data that we do have actually access to. Okay, and indeed we're going to try, and so let's see how that's going to work. Okay, so this real world is called validation. Okay, so the setup starts off the same. Okay, we have our data set. We have our data set Dn. Okay. Now, here's what we're going to do. We want to be able to evaluate the final hypothesis. So we need a test set of, let's say, size k. So what we're going to do is we're going to randomly split the data set into two sets. Okay. We're going to randomly split the data set into two sets. One of size k, so let's call that dk, and the other of the remaining points of size n minus k. So let's call that dn minus k. So this is a random split. Okay. So in other words, randomly choose k points. Okay. Put it into a set here. Okay, and I can even list them x1, x2 up to xk, and the corresponding y values are there, and I have my data set of the remaining points. Okay. Okay. And what have I done? What I've done is I've sort of simulated, I've created this setup, except where I had the data set before, I have a deficient data set, a data set that is missing k points. So we will in fact call this a deficient data set. But everything else that we saw here now can be run. Okay. I can send this data set through my hypothesis set and my algorithm and produce a final hypothesis G. Okay. But is this final hypothesis going to be the same as this final hypothesis? No, because this final hypothesis was picked using all the data. This final hypothesis is picked using the deficient data set. So we will label this the deficient hypothesis, G minus, indicating also the fact that because it was picked using fewer data points, we expect it to be worse. So we really do expect this guy to be deficient. Okay. Not only was it trained on fewer data, but it probably doesn't perform as well. Okay. And we're interested in the out of sample error of my deficient hypothesis, E out of G minus. Okay, and we run exactly the same game. Okay, so I have k test points, and these really are test points because remember the data set, the original data set was generated IID. Okay, and then I randomly split it. So these are randomly generated independent test points, just like they were here. Okay, so I can take this G minus and evaluate them on this data set and get E1 of G minus, E2 of G minus, and so on up to EK of G minus. And I can evaluate, I can compute the errors that my deficient final hypothesis is making on this set of k simulated test points, real test points, but they came from the data set. Okay, and I can then compute the average. So the average 1 over k, the sum from k little k equals 1 to big K of E little k of G minus. Okay, and now I have my estimate of the out of sample error. Okay, and let me add some terminology here. Now, even though this is technically speaking, just like here, and a test error for this G minus, we typically call this the validation error. So this is called eval. Okay, the validation error. Okay, and this set, okay, it's technically functioning in exactly the same way as this test set, but we don't call it a test set for the only reason that this set was created from the data set. So this guy is called the validation set. Think that I'm using this set to validate whether or not G minus, the deficient hypothesis, is good. Okay. Now the rest of this discussion also continues. There's no way in which this data set of k data points is different from this test set of k test points with respect to this hypothesis. So this validation set with respect to this deficient hypothesis functions in exactly the same way as this test set with respect to the original final hypothesis. So this validation error, okay, is an estimate, okay, of this validation error is an estimate of E out of G minus, just like the test error is an estimate of E out of G. So the expected value of the validation error, Okay, now expected value with respect to what? With respect to regenerating of these test points. So that's what this expected value was. So you could think about, if you fixed this training set but then randomly regenerated test points, the expected value of the validation error is actually E out of what? Of G? No, of G minus. Okay? And similarly, the variance of the validation error, is indeed 1 over k, times the variance of what? Of E of G minus. Okay? So all the same analysis applies. Okay, nice. All right. Okay. Now we're going to sort of analyze this validation scenario, but I'm just going to throw out a question. So, I split the data into a validation set and a training set. I got G minus, okay, and now I have an estimate of E out of G minus, okay, and I can even see that the variance of this estimate, the variance of E validation is dropping in the same way that the variance of the test error is dropping. Okay, so, what's wrong? If I want a better and better estimate, why don't I just set k to be as large as possible as I would have liked to do here? Okay, so is there anything wrong with separating out the data into a, by the way, this is called a training set. This is called the training set. So is there anything wrong with separating out the data into a training set and a validation set? Okay, I'll give you a couple of seconds. Pause the video if you want. Think about it. If you're coming back just for the ride, yes, there is something that could go wrong. Okay, so what would happen? Let's take the extreme case. What would happen if I set k equal to n? Then I have no data to train on. Okay, so it means that my G minus will be just a random hypothesis picked from my hypothesis set. There's no criterion on the basis of which to pick a different hypothesis. Okay, and so I would expect that E out of G minus would become very high. Okay, so let's compare with here. G is the fixed final hypothesis, and now if I generate more and more test points, this guy doesn't change. Okay, G stays fixed. Here, on the other hand, if I put more and more data into the validation set, E out of G minus is going to change. The expected value of E k of G minus, the expected value of the error that G minus makes on a data point is going to rise because I'm picking it on the basis of fewer data points. It's a truly deficient hypothesis. Okay, so if k goes up, if you put more data into your validation set, E out of G minus will go up. So in other words, you'll be producing a worse and worse final hypothesis, and this will be indicated by eval going up. Eval will go up. Because remember, eval is a decent estimate of E out of G minus. Okay, and so yes, okay, yes, you might get a better estimate of the E out, but it's going to be a better estimate of a bad quantity. You'll basically be saying that this is a hopeless hypothesis because you've traded on less and less data. Okay, so there's a trade-off. You can't just throw data into the validation set. You're going to pay for it when it comes time to pick the deficient hypothesis because you're picking on the basis of fewer data. But now let's also look at the variance. Okay, so the variance of eval is made up of two terms. The 1 over k term, okay, certainly if k goes up, is equal to 1 over k times the variance of E of G minus. Okay, so certainly the k term will go down. So this will drop. So we're looking at the situation where k goes up, you increase the validation set size, so this will drop. Okay, but this guy is interesting. So we already argued that this hypothesis gets more and more deficient, which means that these errors get larger and larger. And it's typically the case that something that's larger and larger will have more and more variance. We're taking the variance of these guys. Okay? So something that's larger and larger will typically have more and more variance. So this guy will tend to increase the variance of the individual errors because they're getting larger, and large things typically tend to have higher variance. So this product, we don't know. It could either drop or it could increase. Okay? And typically what happens is, okay, it drops first and then it increases. It drops first because you're getting the benefit of a more and more accurate estimate. The 1 over k dominates. Okay? But then it starts increasing because this now starts giving you diminishing returns when you go from k to k plus 1. But when you go from k to k plus 1, you decrease the the data set by 1, and when the data set is small, decreasing it by 1 is a big deal. And so then this variance of the individual errors goes up a lot. Okay? So let me show you that in a picture. So if this is K, the size of your validation set, okay, the number of validation points, okay, and on this axis I'm plotting various errors, okay. So then your out of sample error for the deficient hypothesis, that's always going to be increasing, because as you increase K, you have less data to train with. Okay, so let me draw it like this. So this is the expected value of eval, okay, which is the E out of G minus. Okay, but remember that G minus is not a fixed hypothesis as you increase K, because as you increase K, G minus is getting worse and worse. So I should really put here G minus of K if I wanted to be more precise. Okay, but now this variance, this error bar in eval is going to look something like this. Okay, so at the beginning, if you pick K equals 1, it's just a wild estimate, and you've got a huge variance. Okay, so the variance looks like this. Okay, it's a huge variance. And then, okay, as you increase K, okay, the variance drops because you're not getting a significantly deficient hypothesis. Okay, so if you take 1 point over here into the validation set, you have a huge variance. Okay, if you take 2 points, you have n minus 2 points, and that's still pretty reasonable for picking a deficient hypothesis, and you have almost doubled, you have halved the variance. So you get a lot of, variance gain for small k. So the variance initially drops, okay, and then once you start getting a more and more deficient hypothesis, the variance of the errors that the hypothesis makes start to increase. Okay. Okay, and this is the variance of E of G minus. And if you think about, what is the true out of sample error, it's not going to be much more than, you can get probabilistic bounds with respect to the expected value of eval and its variance. Okay, sorry, this is the variance of eval. Okay, and if you add these two quantities, the variance plus, so let's say the square root of the variance plus the expected value of eval, it's going to look something like this, a picture that we have seen before. Okay. So as you increase the size of the validation set, your estimate, your E out, is dropping. E out being the validation plus its variance, okay, is dropping, and then it starts increasing. It's dropping because you're getting a more and more accurate estimate of E out. And then it starts increasing because the function gets worse and worse. Okay. And so there's an optimal validation set size, K star. Okay. And we find, as a rule of thumb, that K star is of the order of n over 5, works well in practice. Okay, so there's a rule of thumb. So there we have a sort of a pretty decent way of estimating the out-of-sample performance of the final deficient hypothesis. So what you do, you take your data set, put 80% into training, put 20% into validation, you get a final hypothesis, and you can estimate the out-of-sample error of this final hypothesis. Okay, good. And I'm going to erase, okay, and then I'm going to be back with the real punchline, Okay. Let's erase fast as quick, bam, bam. Try a speed erase. Okay. Okay, so now your client gives you a data set. Okay. I want to emphasize that the primary goal is to always output as good a final hypothesis as you can for your client. Okay, so primary goal, output best G. That's the primary goal. Okay. Now, we know that there's this two-step process. Okay. So we output the best G we can, but that doesn't mean that we only look at the in-sample error. So we would like to to understand what is the out of sample error of your final hypothesis. So you can think of that as a secondary goal. It's important, but it's really ideally you want to give the best hypothesis and then also an estimate of the out of sample error. So secondary goal, okay, estimate E out of G. Now the main reason why we estimate E out of G, okay, is so that we know whether or not we succeeded. And if we succeeded at the end, we are going to deploy G. So we want to deploy the best thing that we can deploy. Okay? And now I want to emphasize that validation is addressing this secondary goal. The primary goal still always remains. And I'm going to now show you that we can achieve the primary goal while still maintaining the whole validation setup. Okay, so we'll call this restoring the data set D. Restoring Dn. Okay, so basically, we're not going to output the deficient hypothesis. Okay? We're going to always output the final hypothesis G. Okay? So, you have your data set Dn. Okay? So let's review what we did with the validation. Okay? So you split it into a training set Dn minus k and a validation set Dk. Okay, good. Okay. Then you get the deficient hypothesis by running your hypothesis set and algorithm on the deficient training data. Okay, so you get G minus. And now what you're going to do is you're going to evaluate G minus on dk and get eval. But eval is for G minus. And we know that eval is approximately equal to E out of G minus. Okay, good. And you can arrange this by suitably choosing k, and we gave you the rough rule of thumb that you should choose k about approximately 20% of your data. So 80% for training. That gives you a pretty good G minus, and then 20% for validation. Okay? And so the output here is going to be eval. Okay? Now, you're actually not going to give your client G minus because it's deficient. Why would you give, even though you have an estimate of its out of sample error that's pretty good, okay, why would you give the guy G minus? So you're going to train on all the data and produce your final hypothesis G. Okay, and this final hypothesis G has an E out of G. Okay, so you can think of all this validation as going on behind closed doors. So the client gives you the data. At that point, you go behind closed doors, okay, and you do your business. Okay, and output G, okay, and eval. Okay. And then when the client says, well, what did you succeed? You say, so you have to give them an estimate of E out of G. Okay, and so what you'll do is you'll give them the validation error as your estimate of E out of G. And, what we need to do is now we need to look at whether that's a good idea. So you are going to give them E out of G equals to eval. Okay. But remember that eval was tailored to estimate E out of G minus. So we're going to come back and we're going to analyze this now. Okay. This process where you produce the final hypothesis as you would have normally done, and then you do the validation solely for the purpose of estimating E out. Nothing else. It's not to output G minus, it's to estimate E out. So take that in. That's important. Okay, so using eval to estimate E out. Let's analyze that a little bit, and let's first see also what are our alternatives. So using eval to estimate E out of G. Okay, so the VC analysis, let's go back to the VC analysis, which said we don't need to do any of this stuff. We've got G, we've got a bound. The VC analysis says E out of G, is less equal to E in of G. This also we can compute, E in of G, if we wanted to, plus, this error bar, which was order of the square root of, dVC over n log n. Okay, so we always have that. But now we're doing something interesting here. Okay, we're doing validation, and so we're going to estimate E out of G using the validation error. But what is the validation error? The expected value of the validation. So the validation error is estimating E out of G minus. Okay, but this is a deficient hypothesis. Okay, now although it's possible if you're it's possible that the deficient hypothesis is better than the full hypothesis. What that means is that when you learned on a smaller data set, you produced a better hypothesis. It's possible to construct scenarios like that. You have to really contort. So if you're in a machine learning setup where fewer data points gives you a better hypothesis, it's time to get out of that game and go and work at McDonald's. Okay, so we're all in over our head when more data doesn't result in a better hypothesis. So it's reasonable, to sort of say that the out of sample error of G is going to be less than or equal to the out of sample error of G minus, because this guy is deficient. Okay, so E out of G is going to be less than or equal to E out of G minus. Okay, and indeed, there's going to be some slack here, and let's see what controls that slack. Okay, well, if k was small, okay, then this slack is going to be very little. So then these two will be very close to each other. If k is very small, the deficient hypothesis will be very close to the final hypothesis trained on all the data, and so these two out of sample errors will be close. Okay, so here, this is controlled by k. And k small makes this tighter. Okay, but now what is E out of G minus? We're using the validation error, and the validation error is a k sample estimate of the out of sample error of G minus. Okay, but G minus is just a single hypothesis, so we can use the single hypothesis Hufting error bar. Okay, so the validation error is an in-sample error in some sense. We're in a verification setting where the validation error is attempting to verify G minus. So this guy is going to be less equal to eval plus order of 1 over root k, or square root of 1 over k. Okay, and that's the single hypothesis Hufting error bar with a data set of size k used to verify. Okay, and so, the question is, which is better? So when do we get a better bound? Now, it's possible for either of these bounds to be the better bound, and you always have access to this bound, and now we have this bound, and very often in practice, this bound wins, because DVC can be large. Okay, so DVC over n can be large, whereas 1 over k is, the size of the validation set, which you can make, it's proportional to n, it's 1/5 of n. So, as long as DVC is bigger than 5, this is sort of winning. Okay, so this tends to be a better bound, okay, for E out of G. Now, why is it a bound? Because E out of G is less equal to E out of G minus, and E out of G minus is less equal to this from the single hypothesis Hufting error bar. Okay, so this is sort of the comparison of the two bounds. Very often this wins, so this gives you a better estimate of E out, and then you have a better way of saying, did I or did I not succeed? Okay, so that's validation used to estimate the out of sample error. Okay, and now we'll erase. Okay, and if we accept, well, we always have the VC error bar, but if we accept that validation is a good estimate for the out of sample error, then one of the most popular users of validation is for model selection. So let's come back and discuss model selection. Let's erase first and talk about model selection. Okay, so model selection. It's a very simple but useful application of validation. Okay, so remember in validation you have your data set dn and you have split it into your training set dn minus k and your validation set dk. So let's call this the training set dtrain, and let's call this the validation set dval. Now, what is the problem in model selection? So imagine that you have models. Okay. Now, typically when we say models, we mean different hypothesis sets. So that's the mode in which I will, frame the discussion. But models can have the same hypothesis set but different algorithms. Okay. So there can be many different ways in which learning models can differ. Okay. So imagine that I have, model 1, model 2, model 3, up to model big M. Model big M, okay? And typically this means that you've got hypothesis set 1, okay, linear models. and you've got hypothesis set 2, you know, neural networks, and you've got hypothesis set 3, you know, radial basis functions, and so on, support vector machines, and etc., etc. Okay, M. So you have, let's say, M different models. Okay, now what's the problem? So you have your data set Dn, okay, your full data set, and if you train your model 1, you get G1. If you train your model 2, you get G2. If you train your model 3, you get G3, and so on, you get Gm. Okay, good. So the model selection problem is, well, you know, I've trained all my models, okay, and now I need to pick one. Which one should I pick? And, you know, what's its out of sample error? Okay, so I pick one. Let's say this guy wins. Okay, so I pick this guy, and I've got E in of G2, and what is E out of G2? So the first question is, you know, why did I pick G2? Okay, and how do I compute its out of sample error, you know, E out of G2? Okay, so, you know, one of the typical applications of this is to think of the supervisor who doesn't know what the heck is going on in the models. So you can think of the models as being black boxes behind closed doors. So the supervisor has M minions and gives the machine learning problem, i.e. the data set, to the M minions and says, go. And the M minions produce, you know, final hypotheses. Okay, now, you know, on what basis should you even pick one of these final hypotheses? Because imagine if this guy was trained with linear models and this guy was trained with the most complicated this and that neural networks. And this guy, you know, got an in-sample error of, you know, close to 0, but you have no idea, because it's behind closed doors, you have no idea what's its out-of-sample error. Okay? And you have no idea or what you think its out of sample error is, and same here. So you need to pick one. Okay? And validation can be an answer to this problem. Okay? So let me show you how we solve this problem in the validation setting. Okay? So, you know, we now don't give my minions the full data set. We give my minions the training data set. So it's very simple. You have your models, M1, M2, M3, and so on, up to M sub M. Okay. You give the training data set to your minions, to your different models, and they each produce a deficient hypothesis. That's the beauty of what's going on, to realize that, well, they're actually producing deficient hypotheses. G1 prime, G1 deficient, G2 deficient, G3 deficient, and so on, Gm deficient. Okay, and now what you can do, okay, is because you had the foresight to save a validation set which they never got to see, you can now you can think of these as finalists, okay, in a competition. So each of these guys, each state has produced a finalist. Each minion has produced their final hypothesis, and you can think of these as entering into the final competition. So these are the finalists. Okay, and now we have a training data set that produced these finalists, and now we have this validation data set which we can run these finalists through. Okay? And they will each produce a validation error. Let me call this guy's validation error E1, let me call this guy's validation error E2, and E3, and so on. EM. Okay. Now let me remind you, what are these validation errors estimating? These validation errors are estimating the out-of-sample error for the deficient hypotheses. So E1 is approximately equal to E out of G1 minus, let us assume, okay? And E2, and you can go and sit down and do all the analysis. E2 is approximately equal to E out of G2 minus, okay? And so on, approximately equal to E out of G3 minus, and this is approximately equal to E out of Gm minus. Okay, and now, simple solution to the model selection problem. Pick a model which got the smallest validation error. So you can think of this as a new hypothesis set. These G minuses are new hypothesis, is a new hypothesis set. So let me define a deficient hypothesis set H minus, which is just the finite collection of hypotheses, G1 minus, G2 minus, G3 minus, and so on, up to Gm minus. Okay, it's a finite collection of hypotheses, finite. Okay, and now I'm going to evaluate these this deficient hypothesis set, okay, of finalists on the data set which I'm calling my validation data set. So I pick one based on d-val. And that's effectively what I'm doing. Okay, so I reduce my models to their finalists, and then I use my validation set to pick one of the finalists. Okay, and what do I get from this? I get that, when I pick one, Okay, so now, even though each validation error independently approximates the corresponding out of sample error, that's no longer the case after I pick. I have to pay a price for picking on the basis of the validation data. So what I will find is that when I pick the best one, let's call it G minus star. So this gives me G minus star, my final deficient hypothesis. Then E out of G minus star will be at most eval of G minus star. Now I'm going to have to apply not the single hypothesis Hufting bound, but I'm going to have to apply the M hypothesis Hufting bound, plus order of the square root of log M over K. Okay, why log M? Because that's the size of this hypothesis set finite, and why K? Because that's the size of my validation set which I left out. And we typically pick K approximately N over 5. So you'll give your minions 80% of the data to chug along. And the nice thing here is you don't need to know what they did. Okay, they just produce the finalists, and you treat the finalists as a new hypothesis set, and you pick one from here on the basis of eval. Okay, and surprise, surprise, let's say you pick this guy, you are making a leap of faith. Okay, what's the leap of faith? You're making a leap of faith that the model which had the best deficient hypothesis, okay, will also produce the best final hypothesis, because just as we talked about restoring the data set, you don't output G star minus. You don't output G star minus, because it's always going to be the case that G star minus. It's always going to be the case that G star trained on all data will be better than G star minus. So you output from here G2. What does that mean? You run model 2 with all the data. So you take model 2, you run all the data, Dn, and can compute G2. Okay. Now, there's a leap of faith here. What's the leap of faith? That's actually a leap of faith. It need not be necessarily the case. So this is perfectly valid, and you have with high probability, picked the hypothesis that the deficient hypothesis that's big, that's best if K is reasonably large enough. Okay, and it is also the case that G2 will be better than G2 minus, or G star will be better than G star minus. That's also the case. What is the leap of faith is that it's not necessarily the case that the model with the best deficient hypothesis is the model that will produce the best full hypothesis. Because think about what these deficient hypotheses are. These deficient hypotheses are all trained on the deficient data. It's possible that the deficient data set, the training set, is right on the cusp of when this model will become spectacular. Okay. And if you had given it that extra K data points, this model would be spectacular, and G3 might be the best. Okay. It's just that when you took those extra K data points away, that really slammed this model. So this model happens to be very sensitive to those K data points. In other words, G minus for this model can be very different to G for this model. On the other hand, this model may be very robust. You can take away lots of data points, and it's not going to suffer too much. So G minus and G are close. Okay. But G minus for this guy, when you take away the deficient, when you take away the K validation points and train on the deficient data, this guy's G minus is much better than this guy's G minus. Whereas if you gave all the data here, this guy would be the clear winner. Okay, so that's a leap of faith, which happens very often in practice. Okay, that when you take away a certain fixed amount of data from all the models, they all sort of drop in performance comparably. It's possible that some models drop a lot more than others, in which case you may end up picking the wrong model. But at least we have a principled approach for model selection. Okay. And now let me show you how we can use this to pick the regularization parameter, which from the last lecture we saw is an important parameter to pick because it is what we have, it's the knob we have to control how much we sort of break the learning algorithm and prevent it from fitting the noise. Okay? And it's an important parameter to pick. Okay? And so, you know, picking lambda. Okay, so picking the regularization parameter lambda, very easy. I don't even need to say much. What's going to be going on? I define models for different lambda. That's it. So my models will all be defined with the same hypothesis set. So they'll all have, you know, each of my models will have the same hypothesis set. So whatever it happens to be, let's say linear models for linear regression. So same hypothesis set H. Okay, same hypothesis set H. And that's perfectly valid. So models can have the same hypothesis set H, but different amounts of regularization. So, you know, you could define a set of regularization parameters starting from, let's say, 0.0001 and then going up in, let's say, multiples of 2. So 0.0002 all the way up to, you know, and then 0.0004 and so on, you know, going up, let's say, to 10. Okay, and that's not going to be too many. Okay, so if I divide, so that's not going to be too many models, so that the error bar for the validation error will be reasonable. And, you know, I can define this as lambda 1, lambda 2, lambda 3, and so on up to lambda m. And I define one model with lambda 1, another model with lambda 2, another model with lambda 3, and so on, lambda m. And I have defined m models, and then I just run model selection. So I train the models with each of their respective regularization parameters, then I validate them on the validation data. Okay, I get the validation errors, pick the model that gave me the best validation. Okay, and now, you know, it's an interesting question whether I should run the model on all the data with to produce the final hypothesis. Okay, and you know, you can do that, and there are slightly more sophisticated things you can do because now that you have more data, usually you'll need slightly less regularization. So you might be able to correct a little bit for the fact that you have more data, you need to break less to get the optimal hypothesis from whatever that model is, whatever that lambda is. Okay, so, you know, there's a lot of interesting things, you know, to think about when it comes to model selection to pick the right lambda and model selection in general, but now you have the big picture of how we do model selection using a validation set. Okay, and let's go back to now validation and discuss an issue that might have been bugging you. So we're done with model selection. Let's go back to validation. Okay, and discuss the general philosophy. So you're going to output G. Okay, and G has E out of G. Okay, and basically what we said was, you know, E out of G is approximately equal to E out of G minus. So if you're using validation, okay, so you can get the deficient hypothesis, and, you know, E out of G is approximately E out of G minus, and then E out of G minus is approximately equal to E val, okay, of, you know, G minus. So E val is evaluated for G minus on the validation set. Okay, and then we just miraculously or just optimistically use that E val for E out. Okay, so this is a chain of equalities, and let's see what it depends on. Okay, so how close is E out of G to E out of G minus? These two will be close when G is approximately equal to G minus, which means that you want K to be as small as possible. So you want you know, this deficient hypothesis to be trained on almost all the data. So you want K to be small, so that n minus k is approximately equal to n. Okay, so you want k small for this to hold. Okay, but if k is small, then your validation set is a small number of data points. Okay, and so the error bar on this validation error will be large, order of 1 over root k. So the error bar here will be large. So to get this equality, you know, tight, we would like to choose k large. Okay, k large. And that's because, you know, the error bar on E val being close to E out of G minus, the error bar is order of 1 over root k. Okay. And so there seems to be a big trade-off here. Okay? I'm trying to estimate E out, and I'm stuck between a rock and a hard place. If I choose K small, I get this equality, but then validation error is useless. If I choose K large, then I don't get this equality, and so this is good. E out or E val of G minus is close to E out of G minus, but who cares? I'm outputting E out, I'm outputting G, so I need E out of G, and this will be far apart, because this is really deficient if K is large. Okay? So the next issue we're going to address is this issue of K. Can I have my cake and eat it too? So is it possible for me to get away with K equal to 1? What about K equal to 1? Okay, that would be a miracle, right? Because if K equals 1, then these two are basically the same hypothesis. This is G, and this is deficient by 1 data point. Okay, but then if K equals 1, this is going to be wild, completely wild. Okay, so this is what we need to address if we're going to try to set K equals to 1. And so when we come back, I'll show you a method for having our cake and eating it, i.e. setting K equals to 1, and that's called cross-validation. The queen of validation techniques. Okay, so let's erase, come back, and talk about cross-validation. Bam, bam, bam. Okay. Cross-validation, or can we get away with setting K equals to 1 in the validation setup? So cross-validation. Or can we use K equals 1? And we saw the trade-offs with K. So we're going to one extreme of the trade-off and trying to get G approximately equal to G minus. Okay, but then we're wondering whether the validation estimate is going to be of any use. So let me illustrate with regression, okay, which I can easily draw. But I want to emphasize that this whole validation framework and model selection applies to any machine learning problem. Classification, regression, logistic regression, and whatnot. Okay, so here's a simple regression problem. You have 3 data points. Okay, so let's imagine 3 data points. Okay, and if you fit the data, you're going to get a line something like that. Okay, so one-dimensional regression. Okay, now if I'm setting K equals 1, I leave 1 data point out, and I'm going to fit on the remaining 2 data points. So let's imagine that I left out data point 1. So let me indicate that by I leave out data point 1. Okay, and I have the other 2 data points. Okay, and since this has been left out, I have to fit those data points. So my deficient hypothesis is going to be this guy. Okay, and I'm going to get an error, which is this guy. Okay, so this is the deficient hypothesis. This is, you can call this G1 of deficient. Okay, so if I call this data point x1, this data point x2, this data point x3, then if I leave out data point 1, I get the deficient hypothesis G1 minus, indicating that I left out data point 1. Okay, and I get an error across a validation error E1. So E1 is the validation error. Is E1. And it is indeed the case that if I take the expected value over the data point x1, that the expected value of E1 is equal to E out of G1 minus. That is true. Okay? That's the whole validation analysis. Okay? The problem with E1 is not that it has the wrong estimate. It's not that it's not estimating E out correctly. It's that it's wild. Its error bar is huge. So it's wild. E1 is wild. Okay? All right. But nobody said I had to leave out E1. I mean x1. Nobody said I had to leave out data point x1. So let's see what happens if I leave out, maybe another data point. Okay, so this is if I leave out data point x2. So I have this guy, that guy, and I've left out this guy. Okay, so I have to, my learning is producing the deficient hypothesis that fits the data that remains in the training set, which is this. Okay, and now I have an error which is E2, okay, and this is my deficient hypothesis G2 minus. The deficient hypothesis I get from leaving out data point x2. Okay, and so the validation error in this case is E2. Okay, and again, E2, the expected value of E2 is indeed expected with respect to the second data point is indeed E out of G2 minus. But it's just wild. And we can do the same thing with the third data point. Okay, so what happens if we leave the third data point out? So we have this guy and that guy, and we've left out this guy. So we have to fit these points. That's our training data. And we incur a validation error, E3. Okay, and this is my deficient hypothesis G3 minus. Okay, and so my validation error is E3, and it is indeed the case that the expected value of E3 with respect to the third data point that I left out is indeed E out of G3 minus. So what these mean is that the data point that's left out is a random test point for the corresponding deficient hypothesis. Okay? But they're all wild. So which one should I pick? And the answer is don't pick any of them, pick all of them. Okay? In other words, average. Okay? So so each of these is a decent estimate of the out of sample error for a deficient hypothesis. Now, okay, important. These deficient hypotheses are all slightly different. So you have G, this guy G, okay, and each of the GIs, GI minus, so G1 minus, G2 minus, G3 minus, and if I had endpoint, they're all sort of slightly different from G, and they're all slightly different from each other. Okay. But here's the interesting thing. I have out of sample estimates for the deficient hypotheses G1 minus, G2 minus, G3 minus. Okay. They are all close to G. So all these out of sample errors are close to the out of sample error for G. So let me take the average. Okay. And they're all wild on their own, but if I take the average, maybe I get a good estimate of the out of sample error for G. Okay. So take the average. And that leads us to the cross-validation, estimate for the out-of-sample error. I'll call it ECV. Okay, and this is equal to the average. Write it in the general case. So here we have just 3 data points. It's the average of, the leave one out validation errors. So it's the average of over little n goes from 1 to big N of E sub little n. So this is called the leave one out error for leaving out data point xn, yn. So it's the leave one out error. Okay. And I just get all the leave one out errors and average them. Okay. So that is my, cross-validation estimate of E out. Cross-validation estimate of E out. Sometimes it's called the leave one out error for this reason. Okay. Now, let's see what's going on. Each of these little estimates is an estimate for the out of sample error of a function that's close to G, okay, and then I'm just taking the average. In fact, theorem. Okay. So let me define, E out of n minus 1. Let me define E out or E out of n minus 1. So what is that? That's the error you expect to incur when you learn with n minus 1 data points. Okay. It's the error you expect to incur when you learn with n minus 1 data points, averaged over data sets of size n minus 1. So you can think that, I generate a data set of size n minus 1, I learn, I produce a hypothesis G sub n minus 1, let's say, okay, and I evaluate its out of sample error. Okay. Then I repeat, generate another data set of size n minus 1, learn what's the out of sample error. And on average, I get some expected out of sample error when I learn on n minus 1 data points. Okay. So, theorem. If I take the expected value with respect to data sets, so with respect to data sets Dn, my data set Dn, for the cross-validation error, this equals E out of n minus 1. So in other words, the cross-validation error is an unbiased estimate of what? Of the expected error you incur when you learn on n minus 1 data points. Now, in reality, you are going to learn on n data points. Okay, you're going to output G. So E out of G, okay, because this is the expected error on n minus 1 data point, E out of G, you expect that to be slightly less than this. So typically, E out of G will be less than or equal to ECV. Okay, well, okay, because this is the error after having learned on n data points. Okay. ECV is an estimate of the error having learned on n minus 1 data points. Okay. And it's a pretty good estimate of E out of G because the k value, these deficient hypotheses only differ from G by just one data point. So these are very close. Okay. And now the only question is, how wild is ECV? And we might think that the error bar is plus order of 1 over root n, because it's the average of n things. The problem is these n things are not independent, and I'm just going to leave it at that. Okay. And I'll just illustrate why they're not independent. So let's look at, for example, E1 and E2. Okay. E1 is, an error on data point x1, y1. Okay, so it's the error on this. E2 is the error, on x2, y2 for G2 minus. But G2 minus depends on x1, y1, which depends on x1, y1. So E1 depends on x1, y1 on the first data point, and E2 also, in a very subtle way, depends on the first data point x1, y1, albeit not that much, because G2 depends on n minus 1 data point. So the influence of x1, y1 is not very large on E2. Nevertheless, it exists. So E1 and E2, these errors are not independent, but they're almost independent. But I cannot give you a mathematical quantification of that. It's very hard to analyze theoretically the variance, for example, of the cross-validation error. But E1, E2, up to En are not independent. Okay, they are not independent, but they're almost independent. So you more or less, in practice, we see that we get, maybe not 1 over root n, but maybe we get like 5 over root n, or something like that. It's very close to being independent. Okay. And so this is a very good estimate of the out-of-sample error, the cross-validation error. And so now you can use this error for model selection, okay, and get k equals to 1. So cross-validation, the queen of validation, is a way to get away with k equals 1. Okay. Now, you might wonder, well, in practice you hear people talking not about cross-validation, but about something like tenfold validation. Okay, so let me tell you what's going on there. So cross-validation. Okay. That is what you should do. Okay. And, if the stakes are very, very, very high, then that is what you should do. Okay. The problem is it is computationally intense. So computationally intense. Okay. So let me show you what's going on here. Okay, so look what happened. With just 3 data points, I have to run 3 linear regressions. Okay? And imagine if I'm doing not linear regression with the pseudo-inverse analytic algorithm, if I'm doing classification and I have to run the bucket algorithm for 1,000,000 iterations. Okay, so I have to, in general, with n data points, okay, I have to do n separate learnings and then one more to output the final hypothesis G. Why? Because I'm never going to output one of the deficient hypotheses. Okay, I'm going to squeeze out that little extra blood, that little extra data points worth of accuracy. Okay, these deficient hypotheses and the cross-validation error, again, let me emphasize, it's just a way to get an estimate of the out-of-sample error. I'm still going to output my final hypothesis G. So I have, n data points, I have to do n plus 1, episodes, or n plus 1 separate trainings. Okay, n of those are on data sets of size n minus 1, and 1 on data set of size n. And typically, each training is not going to be less than, linear in n, and sometimes it can be even worse. Okay, so this is immediately an O of n squared, algorithm, process. Okay, and typically there's some exponential dependence on the dimension. So imagine if n is 10,000, this is already, 10 to the 8. Okay, so it can be, and that's heavy. It's very heavy. So, what does tenfold cross-validation do? Tenfold cross-validation says, okay, don't leave out one data point at a time. Leave out 10% of your data at a time. So if you have all your data, okay, you leave out 10% of your data. And so there are 10 separate 10%. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so you leave out 10% each time. Okay, so it's sort of, and you could do instead 20-fold where you leave out 5%. Okay, so it's now getting back, it's getting closer to validation, except that in validation, you leave out 20% of the data and you're done. Here what you do is you leave out this 10% of the data, okay, and you get a deficient hypothesis trained on here. So this is training. So then you get, let's call this the first fold. So you get G1 minus and you evaluate it here. Okay. Then you leave this out and train on the rest and you get G2 minus, the deficient hypothesis for the second fold. And you evaluate it on here. So you'll get E1, then you'll get E2, and similarly you'll get E3, E4, E5 up to E10. Now you take the average of those. Okay. So it has a slight advantage over just plain old-fashioned validation, which leaves out just one set and then goes. It's still the case, it's still going to be the case that you're evaluating now, the out-of-sample performance of a very deficient hypothesis. Okay. So it's not close to G. You're 10% away in some sense. You're using 10% less data. Okay, but that's much more efficient. Okay. Instead of N separate trainings, you just do 10 separate trainings, much more manageable. There's another situation in which you can run cross-validation, and that's when you can compute the cross-validation error analytically. And you can compute the cross-validation analytically for linear models in linear regression, even regularized linear regression. So regularized linear regression, you can compute ECV analytically. So I encourage you to read the book if you're interested, and you should be interested, otherwise why are you taking this course? Okay? And what that allows you to do, if you can do it with regular linear regression, you can compute this guy analytically. It means that you can compute ECV of lambda 1, ECV of lambda 2, and so on, and then pick the best lambda efficiently for linear regression. And so one thing to do for classification is to use regression for classification and pick lambda, let's say, in your regression for classification setup, okay, using the analytic formula. Okay, so go and look at that. And what we're going to do, okay, is we're going to go and look at some data. Okay, so I'm going to show you the problem. Let's erase. So let's see cross-validation in action. On the digits data, real data. Wow, what kind of a person is this who's showing real data in a theory class? Well, you have to link to real data because machine learning, while a theoretical discipline, has to be connected to practice. Because if you can't do things in practice, there's no point doing the theory. Okay, so we're going to combine all the things we learned so far, well, most of the things we learned so far, and see it in practice on the digits data. So starting with, we're going to use the digits data. So it's real data. And remember, the first thing we learned about the digits data is get features. So we're going to use, symmetry and intensity. Okay. And then we're going to, separate with a linear model, a linear perceptron. Okay, so perceptron. So, the features that we have obtained are, 1, x1, x2. Okay. And so what we're going to do is now see what happens when we use the nonlinear transform. And we're going to use the fifth order polynomial transform. So, this is going to get pumped up to, 1, x1, x2, x1 squared, to x2 squared, x1 cubed, to x2 cubed, all the third order terms, x1 to the fourth, to x2 to the fourth, all the fourth order terms, and then x1 to the 5, to x2 to the 5, all the fifth order terms. Okay. Now it turns out that there are 20 dimensions, so DVC is 21, so there are 20 dimensions. 20 dimensions in the Z space, so in the transform space. So then you say, wow, that's going to be, we have a lot of digits data, but still, looks like that's a lot of flexibility. And it turns out that it may be a lot of flexibility. So we can define a set of 20 models. Okay? So I'm going to use validation, specifically I'm going to use cross-validation to do model selection among 20 models. Okay? So, validation. So I'm going to define 20 models. So M1, M2, M3, up to M20. And what's this? M1 is just using 1 x1. So I'm just using one of my available 20 features in my Z space. So this is just using 1 x1. And then M2 uses 1 x1, x2. Okay, well, let's call these, let me actually call it Z1. Okay, so this is Z1, Z2 up to Z20. I'm going to use Z1, Z2. And M3 uses 1, Z1, Z2, and Z3. And so on. And M20 is the classifier that comes from all the 20 points. Okay, so now how am I going to pick which model to use? I.e., how am I going to pick how many features to use? Okay. Cross-validation. Cross-validation to pick one of these models, MI, okay, i.e. pick number of features. Okay, so let me turn on the slides and just show you the results. Okay, so wow, look at the digits data. Okay, now what we're showing here is a version of the digits problem where we're asked to separate, to classify between 1 and not 1. So it's reduced the 10-class problem to a 2-class problem. Okay, so that we know how to handle 2-class problems. And there are way more red X's than blue circles because there are roughly 9 times as many, not ones as there are ones. Okay, now on the right, we are showing, on the x-axis, we are showing each model. So number of features used, okay, different models. And you see the blue curve, the in-sample error is going down. It cannot go up. So as you add more and more features, as in your polynomial transform, as you add more and more expressibility, more and more complexity, you get in-sample error getting smaller and smaller. And ultimately, we actually achieve in-sample error 0. Okay. Now look at the black curve. That's the cross-validation error. So that's the cross-validation error for each of the models, and it goes down and up, just like the out-of-sample error. Now it's true that the red curve, the out-of-sample error, is related to the blue curve by the VC bound. Okay, but that's a very loose bound. Look at how nicely the black curve tracks the out-of-sample error. So that's the power of cross-validation. Okay. Now we're going to consider 2 scenarios. The first is you go for the in-sample error. So you pick the model that minimizes the in-sample error, which is obviously going to be model 20 that uses all the features. And the other is we're going to use cross-validation. And you see the cross-validation error is minimized at something like 5 or 7 features. So let's pick 6. So we're going to compare model 6 with model 20. Okay. And there you have it. Minimize the in-sample error with all this power. Okay. Even though we have a lot of data, look how it has overfit. Okay. It's got in-sample error 0, but clearly there are islands of nonsense going on. Okay. Nevertheless, the in-sample error is 0, and the out-of-sample error is only 2%, 2+%, and that's the VC error bar. So the out-of-sample error is far from the in-sample error. Look at the cross-validation solution. Wow, beautiful that is. That's the best separator we've seen so far for the digits data. Okay, and the in-sample error is small, and the out-of-sample error is 1.5%, and that's the best we've seen so far. So I'm laying down the gauntlet. Now, when you get your turn at this data, with simple features and simple polynomial transform of 5th order, but that's dangerous. Okay, as you can see from the left. Okay, but using validation to pick the number of features to use, boom, 1.5% out-of-sample error. And for this problem, you might be able to get 0.5% out-of-sample error. So there's some space for improvement, and that's what you guys are going to work on. Okay, but now let me summarize. So we've mostly been covering the theory, the foundations of learning, and we're basically done. We're at the end of chapter 4. We're done with the foundations. Okay, and then we're going to move on to techniques. That's our next big goal. Okay, but the foundations will always be there. So let me tell you what those foundations are. We formulated the learning problem. We set it up. We asked, is learning feasible? That brought in the theory and the 2-step learning. Okay, and then we said, okay, how do we do it well? How do we do it now with the linear model? Can we? Okay, so then we introduced classification, logistic regression, and the linear model. Very powerful. Okay, because it has the link from E into E out, and then we addressed, can we get E in small? The nonlinear feature transform. Be very careful. Good features, always a good idea. Symmetry and intensity, always a good idea to get good features. Okay. And lately we have been talking about overfitting, and that is very important. That's what separates the professional from the amateur. You have to get a grip of overfitting because there's always noise. And we have 2 tools to combat overfitting: regularization and validation to sort of, give you a reality check on what's the out-of-sample error. And as long as you're selecting between a limited number of models, validation can work wonders. And so, hopefully you'll have fun with all this theory when it comes time to implement on the digits data. And I wish you best of luck, and I hope you can beat 1.5%. And with that, I'm checking out. Till next time.